Everyone. Today we have one of our former students, Tugtekin Turan, who got his PhD degree last year under the supervision of Engin Hoca. And today he will talk about his recent work on acoustic and language model adaptations in privacy-preserving dialogue systems. Yeah, the stage is yours, Tugtekin.
Thanks. Welcome and good morning to everyone. My name is Tugtekin, and today I am trying to introduce my recent research during my postdoc stay at INRIA, which is based on automatic speech recognition systems. Maybe before starting, it is useful to introduce myself to your audience. After I graduated my undergrad degree, I started my research at Koç University with Engin Erzin, and at that time we were dealing with some bandwidth extension and speech enhancement problems. Then I defended my thesis in 2013 and started my PhD again at Koç University with Engin Erzin. At that time, I slightly changed my research topic, and I actually investigated some wearable computation problem. And my question was, is it possible to capture some eating related activities using on-body sensing? And I use throat microphones as on-body recording systems. Then after my PhD, I started my postdoc research in France. I am specifically working for a Horizon project called Comprise. Comprise stands for cost-effective, privacy-driven voice systems. And my duty is over there working speaker-adapted acoustic and language modeling systems. So today, my talk will be into two separate parts. In the first part, I will focus on acoustic model adaptation. In this actually case, the specific question is how to provide a decent quality for different type of users in ASR system. Normally, our current dialogue systems are including some supporting some few native languages, but for especially people for accented or non-native speakers, this becomes somehow problematic in terms of performance and accuracy loss. So my first actually problem is to compensate this performance drop coming from accented and non-native speakers. In the second part of my talk, I will focus on language model adaptation. At that time, my actually question was if we have a privacy removed text, I mean, if we remove sensitive information from the transcriptions, how to actually obtain better language model over clean test conditions. I mean, as you expect, if you remove some private data into the from the transcriptions, so we expect that language model and grammatical structure is somehow disturbed. So in the second part of my talk, I will investigate some solutions to compensate this performance loss. Okay, let me start the first part of my talk. Yeah, as all of us are familiar that voice systems and the dialogue systems especially are widely used for our many daily tasks. Some of us maybe are using every day for maybe including finding locations, capturing some news, or for example, United States, it is also started to be used bookings or restaurant kind of reservations over voice interfaces. But we have a big problem here. The performance is not good for speakers whose characteristics actually don't match with the training speakers. Actually, this is number one problem of any machine learning system, because we assume that the data coming from training and test should have some common statistical properties. Otherwise, it creates some mismatch, which drops the overall performance. And in ASR, in automatic speech recognition, accent can be regarded as one of the most important factors for this mismatch. And as I said, current models have a dramatic loss, especially with people with strong accents. In the literature, speaker adaptation is not a new problem. It was actually proposed, some effective methods were proposed before, but research specifically dedicated for non-native or accented speech is not enough. So in this actually part, I try to solve this problem, and I actually introduce a different kind of speaker embeddings, which is based on X vector like architecture and trained to identify several accents. On the right, we can see a small diagram how I try these speaker embeddings. Here I am feeding some input features. We can call those as some spectral features, MFCCs or filter banks. And after some frame level and segment level operations, I extract a speaker embeddings. I call it as accent embedding here. I extract these embeddings and I am actually giving them as auxiliary inputs during acoustic model training. And the network, the overall network, is trained using the accent label. So in this case, I am forcing the network to learn some characteristics of accented speakers. And in this actually approach, there is no need for transcriptions for accented speakers. Only we need some labels to train this network. Here, there's a detailed actually diagram of this network topology. It is TDNN-based, time-delayed neural network-based topology. We can consider it as one-dimensional CNN. So it can model some short-term context. Here in this frame level is acting like RNN kind of processing. And after there's a pooling interleaving between frame level and segment level. And the segment level can be regarded as some feed-forward neural network. And I am extracting these accent embeddings from the last hidden layer. It is also possible to extract in other feed-forward neural layers, but I got the best actually performance over the last hidden layer. As you see, the output is a softmax. So the alpha 1 starting to alpha k represents different accents. So this network can be seen as a classifier for accented speech, and I am extracting some speaker embeddings from the last hidden layer. So as data set, actually, I am using native, non-native, and accented samples together. For accented samples, I am using VoxForge dataset. Here, although their native language of British, Indian, and Australian people are English, but I call just US English as native here. So these three are regarded as accented speakers. And for German accented English, I call it as non-native speakers. For them, I am using Vermable. It's a German data. For native and non-native German English, I am using Vermable dialog data, dialog corpus. And for the accented samples, I am using VoxForge. VoxForge is a crowdsourcing data set. People are recording their own voice using their computer, and it is stored online. So it is not control data. It's somehow challenging, but it gives diversity to us. But Vermable is a control data. It is dialog data with very actually special purpose of tasks like booking or reservation kind of task. So here in the test part, and in the test part, I'm using 25 speakers for each group. Here, the numbers in parentheses represent the duration in hours. I also use extra adaptation split. Again, it has 25 speakers coming from each split, and it is 1 hour per each accent or non-native data. During acoustic modeling, I am using Kaldi speech cognition toolkit, and I am using chain type of acoustic modeling. It is, we can consider it as hybrid DNN HMM models. I am using MFCC spectral features over 25 milliseconds. And the training is actually based on discriminative training. So normally we are in neural networks, we are using cross entropy loss, but in speech modeling, we are actually using conditional probabilities. So discriminative training based on the conditional probability loss instead of KL divergence of or cross entropy. So for decoding, I am using n-gram language models trained over just native data with a limited number of unique words here. And for the embedding model training, I used all the utterances coming from both native and non-native accented speakers, and I extracted 512 dimensional accent embeddings over half-second frames. As objective metric here, I am using word error rate. This is widely used in speech recognition area. It is an error metric, so less is better. First of all, I actually integrated the traditional I vector approach and X vector approach for comparison. Here in the first part of my experiments, I only use native US English for training my models. But the test is performed over both native and non-native speakers as well. I didn't use any further adaptation data. In this case, on the first row, you see the results coming from just spectral features. I didn't use any embedding. In the second row, I am using I vector-based embeddings. And on the third row, I am using X vector-based embeddings. And the final fourth row are the results of my proposed accent embeddings. So in all cases, both non-native and accented speakers, I actually obtained significant improvements using this accent embedding. In the second part of my experiments, I added the adaptation data that I present in the dataset section. I am using 1 hour of data per each accent. These are transcribed data, but with distinct speakers. So adding this and combining with my proposed accent embeddings actually yield the best result in this case. I also put a visual comparison with traditional I vector embeddings. This is a TSNE projection, 2D projection. And on the right side, you see the visualization of I vector embeddings, and here different colors represent different accents, including here the bottom US native English. And as you see on the left, the proposed accent embeddings can actually distinguish accented speakers better than I vector embeddings as expected, because I am training these embeddings based on their accent class tags, so which helps better ASR performance at the end of decoding. I also tested the word error rate reduction performance over different group of speakers. Here I divided my test speakers into 5 different groups and sorted them by increasing performance. So the actually higher groups like G4, G5 can be considered as heavy accented speakers. So these are ranked from easy to hard to recognize order. And on the actually red line, you see the performance is better when I add 1 hour of accented speech per each accent. And the blue line represents that's just native only training. And in any case, I observed word error rate reduction with both conditions, both experimental cases, and I obtained better reduction especially for hard to recognize speakers like group 4 and group 5 speakers. So let me conclude this section with some take-home messages. In this part, I investigated accented speech recognition using some speaker embeddings, and I show that these kind of embeddings can give better characteristics than traditional I vector embeddings. I am simply appended these speaker embeddings during acoustic model training on top of MFCC features. and I actually combined these accent embeddings inside Caldi's chain lattice-free maximum mutual information training. And this method also could be extended as fully unsupervised case. I mean, instead of using transcriptions of additional adaptation data, we can use a semi-supervised training scheme. And in this case, we don't need any transcriptions or labels of accented or non-native speech. I did some initial experiments using this semi-supervised case. I didn't put the results, but I obtained some promising results using this scheme. I am up to now, I did experiments with limited number of languages and accent spots. Some more are right now ongoing. For example, I am right now dealing with a Latvian data set and some Russian accented speech. I am also doing some experiments using other languages. So let me start my actually second part of my talk, which is based on language model adaptation. And in this part, as I said, I am dealing with some privacy removed text, some sensitive information are removed from the input data. And in any ASR task, we are using statistical language models trained from a similar domain text. But as I said at the beginning, the performance is reduced when we disturb the grammatical or lexical characteristics of training and test data. But in any privacy-preserving application, we should train language models over private text. But during the test time, everything is based on clean data. So as expected, privacy removed data unlikely match with the clean distributions. So my aim is here develop an adaptation approach which covers some potential variations in vocabulary changing. To do that, I am introducing class-based language model into my ASR problem. This is not a new scheme for language models, but it was primarily used for insufficient data problem in language models. In this approach, actually similar words or tokens are categorized into different classes, and for each different word class, we are training a sub-language model and integrated them to obtain a final language model. So if we have enough number of data, we define some alternatives of this data into our language models. For example, different days in a week. If we don't have enough number of samples from containing each day of the week, we are adding some alternative the day name into some predefined class. So this actually approach is also work well for out of vocabulary problem. Here you see a block diagram of my approach, and from the seed language model coming from input data, I obtain some hypotheses, and using the class definitions, I actually predefine some class definitions. Combining these hypotheses with class definitions, I am obtaining class-based language models, which eventually yield us better adaptive language models. So mathematically speaking, the task of any language model is to predicting some estimates of word sequences. But in class-based language model, we define a mapping which maps sequence of words, Ws, to a sequence of classes. So roughly speaking, without loss of generality, we can model a bigram language model using this equation, as all of you are familiar. And in the word class idea, this probability of a word sequence will be replaced by mapped version of class-based language models. So here, following the maximum likelihood principle, we can easily count this probability of W1 given C1, or probability of Ci given Ci minus 1, just like what we are using in normal n-gram modeling. But in this class-based language models, we are replacing this probability of word sequences with some class definitions. So let me show how I integrate this idea into my Kaldi speech cognition toolkit. Actually, Kaldi is modeling everything under finite state transducer representations. So all the features, results, language models are represented some finite automata. So to integrate this word class idea into Kaldi, I first create some language model with defining some specific class entries. Those are mapped to name entities in my case. So as you see in this first figure, the state starting from 0, we have some any words here which can become here. And after state 1, there are 2 alternatives in this example, from to, and we have a city name. This is sensitive information here. So I block the city name here as a class entry. In the second part, for each tags, each tokens here, I create individual language models, sub-language models for different classes. Here you see for city name example, I have some alternatives like some German cities, some other cities we can put on top of that here. In my experiments, I regarded them equiprobable, but it is also possible to define some probabilities depending on the application. I mean, if any developer, for example, using this idea and developing a public transportation of Istanbul, for example, can define the locations or bus stops depending on the accuracy probability. But in my experiment, I didn't do it. I actually regarding all these different word classes as equiprobable. At the final stage, I am inserting these sub-language models to get the final language model. So you see these are integrated into final case. So all the trick is here is modeling the grammar FST. This is finite state transducer FST. So first of all, I create a ARPA-based language model, then compile it to generate finite state transducer. And then I am inserting these class-based language model ideas on top of these grammar finite state transducer. So for the data set of this approach, I used AMI meeting corpus. This is dialogue-based data set. It is a huge data set recording with different types of microphones, but I only used recordings captured by closed-talk headset microphones because microphone array kind of distant speech actually didn't give me good results. I only captured data with closed-talk headset microphones. Here on the right side, you see the duration of my data split. In total, I extracted 682 sessions from AMI data, and during the experiments as objective metric, I used Perplexity and again word error rate. Let me quickly introduce how I remove privacy or private content from the input text. So to solve this actually problem, I use name entity recognition idea. This is a simple idea to identify and locate sensitive words into the text. Here I put a sample paragraph using some predefined categories here, like location, date, or organization. It is possible to identify these entities into my text. In my experiments, I am using 4 different categories as name entities. And this my dataset AMI corpus also giving some name entity labels. That's why I actually use this dataset also. But AMI only provides 4 different types of name entities for location, organization, person, and miscellaneous. Here, miscellaneous may be date or money, kind of other related text. So I am using 4 different name entities to extract sensitive words. Here I am presenting perplexity and word error rate of my test split. Perplexity is widely used in many NLP tasks. It is simply defining the complexity of any language model. So less is better again in this metric, just like a word error rate. In the first row, you see the results coming from clean data. So there is no any transformation or any class-based integration here. Using clean text, I obtained 82 perplexity and 23.6 word error rate. And if I removed all these private content from the text, you see the results are actually quite changing, and the errors are increasing here. After class-based integration, I obtained word error rate just as close to my baseline model, which is good. But by the way, I am using name entities from training text. So maybe in a real application, name entities coming from a separate data set. But in my experiments, I use also name entities from training data. I couldn't measure perplexity results after class-based adaptation because, as I said, I am modifying a grammar transducer, but perplexity is only calculated over, for example, ARPA-based language model. So first of all, I have a language model, then I compile it as a finite state transducer, and I am doing some class-based modification on top of that, so I couldn't calculate any perplexity in this class-based adaptation. I also investigated some neural language model schemes. Inside Kaldi, Kaldi doesn't allow to use neural language models in the first pass decoding. So first we need to use n-gram language models, obtain some lattices, and over those lattices, we can do some rescoring over second pass decoding if we want to use neural language models into Kaldi. So I investigated LSTM-based language model. On the first row here over clean lattices, you see we have slight improvements on both word error rate and perplexity side. And again, over privacy removed text, we have little improvement. And after using class-based lattices, again, we can put some slight improvements on top of that. So we can conclude that class-based adaptation with neural language models on second pass decoding will yield the best results in my case. Let me conclude also this session and also my presentation. Here today I tried to introduce you some adaptation problems especially for accented and private. I think these are essential for any dialogue system as well, not just only for privacy preserving applications. So in the first part of my talk, I was focused on how to provide decent quality for multiple speakers in a multi-accented ASR task. I investigated a different type of speaker embeddings to improve acoustic modeling. These speaker embeddings represent the accented or non-native speech characteristics better. In the second part of my talk, I introduce you to language model compensation over privacy removed text, and I investigated word class idea into the existing Kaldi's tools just by modifying this language model transducer inside Kaldi. So this is the actual end of my presentation. I removed all the mathematical and boring stuff to catch your interest in this morning session. I hope you enjoyed my presentation. And now I will be happy for answering your questions or comments. Thank you.
Thank you, Tugtekin. So these are really important problems which have these practical uses as well. So it's very good to hear your work. So let me just first ask the audience. So do you have any questions, comments, maybe suggestions?
Yeah, by the way, I don't know, are your audience is somehow speech or ASI related community, or you are doing some other deep learning problems? I actually don't know your community, so maybe, yeah, I try to keep it everything simple, but maybe for people coming from not coming from speech community, these ideas not easy to maybe capture. I don't know. I don't know actually your actually your question.
Tugtekin, in the second part, you present some perplexity results. Under the privacy preserving conditions, perplexity is increasing significantly. Can you elaborate on that? Is it something good and expected or not?
Yeah, this is actually not good. We are not. We don't actually want this higher perplexity. But yeah, if we disturb the lexical or grammatical structure, I mean, if I replace some words with their name entity tags here, so we are actually disturbing the language model. So this is not wanted case, but so these are somehow expected. Again, it depends on the actually distribution of name entities into your input text. I mean, if your text contains too much sensitive data, here we should expect much higher perplexity in this case, and also much higher error rates consistently. This performance drop, performance reduction, is mainly depend on the number of name entities into the input text. And yeah, as you said, these are somehow expected if we disturb the grammatical structure. I don't know, is it convincing for you, or
Yeah,
To
I
take
think.
in, why LSTM? Why do you use LSTM? Like, why not some other like simpler models? I mean, how do you know LSTM is not an overkill?
For neural language models, actually, RNN-based language models are widely used. Nowadays, transformers are very popular, but it is not easy to integrate transformer-based idea into ASR task because training a language model is not enough. So we should somehow integrate it to speech cognition idea. And until now, the only idea that we have is rescoring. I mean, we should have some first pass lattices of words generated traditional n-gram language models, and using a neural language model idea, what we have do right now is to rescore some tuning those lattices over second pass. This is called second pass decoding after n-gram first pass. So that's why I actually investigated LSTM based model. This is not state of the art, but yeah, for ASR community, only we have right now for neural language model is either RNN or LSTM based language models. Transformer based ideas actually has not yet integrated into ASR community. That's why I investigated this. Maybe if I use this GPT or BERT, like these are very popular right now, language models, I expect much more better perplexity in this site. But yeah, I am approaching the problem not NLP side, somehow speech side. So my proposed solution should be somehow integrable under speech cognition hypothesis. So I just only investigate here LSTM-based language models as a neural language model.
Thank you.
So to Tugtekin, I have a question about the first part. Actually, at the end, you mentioned that this can be extended to the unsupervised or semi-supervised setting. So can you talk a little bit more on that?
Yes, sure. Here, as I said, I have also a distinct adaptation set. Again, 25 speakers for each accented or non-native speech, and which correspond to 1 hour speech. And here I presented you some results. In the first part of my results, I didn't use this adaptation data, sorry. I trained my models using native English and tested using both native and non-native. In the second part, I added this adaptation split into my acoustic modeling, and I see there is a huge performance increment. But this data is transcribed data. If we use a semi-supervised scheme, we can capture these transcriptions using semi-supervision. We can get those labels and integrate into acoustic modeling. This is also possible. So in this case, we don't need any labels or transcriptions coming from accented or non-native speech. I mean, if you have a model trained over just native data, I propose that using this strategy, you can extend this idea, which can be covered these non-native or accented speakers. So using semi-supervised scheme, this idea becomes fully unsupervised. So only you need is just labels of accented data, just labels, no transcriptions. And all you have transcriptions are coming from native English. So we can find many data sets available just like this setting. And using my proposed approach, this kind of ASR task that only supports native English can be extended to be supported just like these kind of different accented speakers. So using this idea, it can be extended like that. And in actually here, as I put a bullet here, and using semi-supervised training fashion, this idea becomes fully unsupervised. That is what I mean by semi-supervision. I did some experiments using this idea, and I got better results, but I didn't put it here.
And an outsider to the field. So while listening to you, I just try to relate some of these concepts to the problems that we are working on in computer vision. Like, for example, we have these photo style transfer problem, where given to image, can we just use the content of one of the images and then translate the style of the second input onto the first one. So that, of course, requires you to separate the content and the style. And it seems in your case, you have the actual language and these different accents. So in a way, these embeddings just provide a way to this separation, I guess. Another related problem I can think of is maybe there are some also works on this. Can you normalize an accent speech into some native speech as well, and then maybe perform ACR after this transformation?
Yes, similar to that idea, I saw some papers using generative models, using GANs.
Yeah.
They can actually generate some, this is reverse part of this kind of problem. Using GANs, some people synthetically generate accented style of speech. And then they edit these accented kind of speech to their acoustic modeling, which actually also populates the data and also gives better performance on accented speakers. So this is somehow yeah, the reverse opposite part of your
yeah, that's
idea,
exactly why I asked this question.
Yeah,
because we have these
yeah.
image to image translation models. So I guess some of the things investigated there can be also maybe translated to your domain.
Because
as well.
yeah, right now current speech synthesis based on research is also mainly done by generative models. So using the same idea, speech synthesis idea, some people actually take that idea to understand the accented speaker characteristics. Then they mimic using this GAN kind of networks. They synthetically generate artificial data, and they then edit their training data just like as accented speech. I didn't investigate, but I saw some recent papers on top of this idea.
Okay, thank you. Okay, any other question from the audience? Okay, then let's thank the speaker again. So really, this was a very nice talk, Tugtekin. Thank you again for sharing your recent work with us.
Yeah, thank you for inviting me. Again, this is very actually exciting for me to meet all of you, and also with my actually previous professors into this meeting. I really enjoyed to present my research. I hope you also enjoyed to learn these kind of somehow different research areas.